We'll proceed in curl in calculus and we will see curl vector field. What we have seen till now. Till now, we have seen curling in vector field. If I have a vector field, then what is a guarantee that vector field would generate a curl? What is a vector field? Vector field is an algebraic vector. Vector field is an algebraic vector. Like one example of the vector field we are giving is the earth gravitational pull. Earth gravitational pull is the example of algebraic vector. How it is? How it is algebraic vector? Earth gravitational pull. Earth gravitational pull is a vector. True. If I drop this, if I mean leave this, then it drops. It pulls exactly in a direction. Okay. Now I am doing like this. It won't go this side. It will again come in a direction. This proves that Earth gravitational pull has a direction. If it has a direction and it has a magnitude, then it is a vector. Earth gravitational pull is a vector. True, because it has a direction, it has a magnitude. Consider this direction is k vector. I mean, this direction is k vector, x axis, y axis, and k axis, z axis. If this direction, if this direction is k axis, then what about this object is falling? If this object is falling, if this object if this object is falling, okay, so so if this object is falling, then it has a direction. This direction is, if upward is k direction, then downward is minus k direction. So this vector has some magnitude, that is 9.8. I believe that if I take the gravitational pull acceleration, then 9.8 and then minus k. What about if this mass is there, and what is the force with which this is pulling? Okay. Now gravitational force is dependent upon the mass, force, not acceleration. Acceleration is not dependent upon the mass, this weight of this mass, but force is dependent upon it. Force in mass into acceleration is force, ma. If that is the case, then if this is the if this gravitational pull is g and this is the mass, then force at which it pulls the item is g into m minus k. Correct. Right. But not true. The gravitational pull is not only dependent upon the gravitational acceleration, mass of the body who it is pulling, it is also dependent upon the distance. So if you are far away from the earth, then pulling force will be less. If you are very near to earth, then pulling force will be high. Means it is inversely proportional to the distance. What is that? So that is minus gm k vector divided by distance square. Since this distance is in direction of the k vector only, so I can consider now k vector as a d vector, d unit vector. If that is true, then if I make it d vector, then one d will come at the bottom, and it will become minus gm d vector divided by d to the power 3, that is the distance, or minus gm r vector divided by r to the power 3. Now this is a vector which has a direction, which has a magnitude, and this vector, the magnitude of this vector is dependent upon the x, y, z, whatever it is. This is a vector field. This is a good candidate for the vector field. Vector field is a numeric vector, static vector, like numeric vector and static vector, but whose components are function over algebraic independent variable. Okay, here it is z, or I can say z minus gm minus gm k vector divided by z square. So that is also is true. What we have seen till now, if I have a vector field, and then if I have a closed loop and I try to calculate integral calculus of this vector field into a direction closed loop. This is also a loop from here to here, here to here on a straight line. Also, I have a closed loop. Okay, if I have a vector field, if I have a vector field, if I have a this is x-axis, this is y-axis. Vector field is in xy plane. If I have a vector field, then what is the vector field's line integral along x-axis from point A to point B and then point B to A? If I add this, then it is in closed loop, A to A to B, B to A. If this vector field is a force field, then force line integral along any straight line or any line is the work done. So, if capital F, that is the representation of a vector field, capital F, on top of it you place an arrow. This is a vector field. So, if this is a vector field dot vector product dot dr vector, where r vector is the line vector. So, capital F vector dot dr vector is the line integral of this vector field. If this vector field is force vector, then force into displacement, this is the work done from point A to point B along this line. Again, point B to point A. Okay, if I add these two, then it will be 0. If it will be 0, because f dot dr vector A to B plus B to A f dot dr vector. If it is not happening 0, if it is happening 0, then vector field is called path independent. Path independent in the sense that the work done or the line integral from A to A or in a loop, the net line integral is 0. Not necessarily that it will be 0, but here it is 0. But now it is saying path independent has more formula. From point A to B, B to A on a straight line someone calculated, but he has to calculate for other shape, other direction also. Point A to B, B to C, C to D, D to A back. In a rectangle also, if he tries in a closed loop, again line integral is 0, then it is again candidate of path independent. Okay. Now, if it is path independent, then if I try for with a circle, if I try with a circle, now it is a point A. Now from point A back to point A in counterclockwise direction. Then if this line integral, if this is the force, then force line integral along the line point A to back to point A, if it is 0 again, then it is again candidate for the path independent. Path independent means the line integral depends upon the lower end and higher end. If lower end is A and higher end is A, reaching from A back to A, you take whatever path you want. Earlier we took straight line path, A to A, B, B to A, or we took rectangle A to B, B to C, C to D, D to A back. Whatever path you take, or we took circular A back to A, whatever path you take, the net line integral is dependent upon lower limit and higher limit, A to A. But how many shapes we will try? We have discussed it. So if that is the case, then we can go for some other fundamental. What we have seen, if our vector field is gradient vector of any algebraic equation, If I have an algebraic equation, consider algebraic equation in x square plus y square equal to a square. This is algebraic equation of a circle. If I calculate gradient vector of this, then it will be 2xi plus 2yj. Means consider that algebraic equation fxy is x square plus y square. If that is the case, then it is 2x. Okay, actually fxy equal to x square plus y square. Means actually the full equation will is x square plus y square minus z equal to 0. It more or less comes in 3D. But anyway, if I have fxy equal to x square plus y square, then its gradient vector is dfxy by dx I vector plus dfxy by dy j vector. That is nothing but 2xi plus 2yj. For if my vector field capital F happens to be gradient vector of any algebraic, you try to, there are billions of algebraic equations possible. You search one algebraic equation for which if you calculate the gradient vector dfxy by dxi plus dfxy by dyj, and it happens to be the vector field capital F, that is f1i plus f2j. Like here, consider that our gradient after vector, our vector field was 2xi plus 2yj. Then I found it. There is an algebraic equation fxy equal to x square plus y square. For that, gradient vector is actually the vector field. If that is the case, if someone finds any algebraic equation and calculate the gradient vector of it and it matches the vector field, then vector field is called line independent, means the net line integral depends only upon a lower limit and higher limit. So if my lower limit is a and higher limit is b, lower limit is a and higher limit is b, then line integral is dependent upon a and b and the vector field, not on the path. Now same a and b, if same a and I had taken a and b on a straight line, if say a and b, if I take on a circle, same b, same a, and calculate the line integral again for this vector field from a to b, the net result will be same because it is path independent. Doesn't depend a and b point is connected by a straight line, or it is connected by a circle, or it is connected by a rectangle, it is connected by a parabola, it is connected by a staircase going up and coming down, not dependent upon. So if that is the case, then it is called, vector field is called path independent. Path independent means if I have a vector field that is passing by, like magnetic field or earth gravitational pull, if vector field is passing by and if I introduce any kind of any curve, any kind of circulation, any curve, then work done from point A back to point A will be 0. You take circle, you take rectangle, you take a straight line, whatever it is. If vector field is path independent, then in a closed loop, line integral will always be 0. Means work done from point A back to point A will always be 0. If this is a mass and this is point A, and because of the vector field this mass is traveling like this and coming back to A, then work done will be 0. This is what is the theorem. If it is not 0, then vector field is not considered as path independent. If it is not path independent, then vector field is not path independent. If this is the vector field, if this is the vector field, inside this vector field I place a curve here, and on the curve I place an object is moving and is coming back to A, work done will not be 0. Line integral will not be 0. If vector field is force, then force into this full displacement will not be 0. If force is vector field is not path independent, what is said? If it is not, if it is not path independent, then there will be work done when it is coming back A to A, because lower limit to higher limit, if it is A to A in line integral, it should be 0, right? It is not 0, means the work done is, there is work done. Then as per the Kern fundamental, this will produce rotation. Very bad. So if this mass is going like this, if mass is going like this, then it will also rotate on its axis while coming back to this place. I believe this is the where it is losing the energy, and that's how work done is there. If it moves unchanged, then there is no curling. Curling means rotation. I mean seeing now only, right? If a mass is moving from point A to point A back in a vector field, consider this vector field is a magnetic field and this is an iron. So iron is deflected like this and it came to a velocity that it came back here. Okay, certainly work done is zero, right? If a mass is traveling and then it is coming back here, then certainly the work done is zero. So is net line integral is zero. But this magnet, this iron, if it is started rotating like this and then it is traveling like this, because this is how it can travel. It is forced to travel in this path. Then when it is reaching back A, then there is a work done by this magnetic field because it rotated, right? It is losing the energy. So curl is nothing but if I have a vector field, under this vector field, if I place a mass, then mass will move as per the vector field. Like water is a vector field. Water force is a vector field. River. This is what example. This is river. Okay, this is river is minus x axis to x axis. This river is flowing. This is one bank, this is another bank, and river is flowing. Now, if I place item here, boat, then boat will move like this. But if boat is, while moving, boat is also rotating, then this vector field is not path independent. It's producing curling, means it is rotating. Or in other terms, if capital F is the vector field, then it has two components, F1 and F2 in xy plane. So capital F equal to F1I plus F2J. If if this is the vector field, oops, if this is the vector field in this direction minus x to x axis, this is y direction, this is x direction. River is like this. I have tilted the river. Okay, if that is the case, then this is F1 of the river and this is F2. So F2 is 0, whatever it is. Now dF1 by dy, how much F1 is changing if I go along y direction and how much F2 is changing if I go along x direction. If dF1 by dy, if dF1 by dy will produce curl in this direction, dF2 by dx will produce curl in this direction. Okay. If that is the case, then they should nullify each other to have the net curl as 0 so that it will be path independent. So if I have a vector field for which curl is 0, then it is guaranteed that it is path independent. So dF2 by dx minus dF1 by dy, that is curling factor of a vector field, rotation tendency of a vector field is 0, means dF2 by dx equal to dF1 by dy, then this vector field is considered as path independent. Otherwise, it will produce curl. What then we saw what is the tendency of vector producing curl inside if this is a river, if this is a river that is flowing and I have taken a circular region, inside circular region if I place a boat and boat is rotating, this proves that vector field is emanating inside this loop. Vector field has a source. Vector field has a source, right? If river is coming, it has a source. If magnetic field is there, it has a source, that is a magnet. One magnet is kept somewhere and then magnetic field is there. If earth magnetic field is there, it has source from south pole to north pole. If gravitational pull is there, then source is at the center of the earth. That's why gravitational pull is there. If there is a curling factor, earth has no curling factor. You can see it. See, I mean it is very energy is very high. So it has no curling factor. It won't rotate. The way you 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 just leave it, it will fall in same way. Okay, it won't rotate. So this proves that curl Earth gravitational force pull has no vector field has no curling factor. But consider it has curling factor. If something is falling from the space and when it enters into Earth atmosphere, it starts rotating also. This proves that at that local region, there some factor has come which has a source of another vector field, and that is causing this rotation. Like I am talking, typically a river does not have any curling tendency, but sometimes you will see when river comes to a deep level, because river flows like, right, sometimes it will have a deep level, sometimes shallow, something like that. Sometimes when it has a deep level, then if some boat try to pass through the river, it will start rotating, swirling, whirlpool it will start making. This proves that this if river vector field has no curling factor, then in local, then if curling factor is seen in the river, then there is a local factor that is coming into the picture. Some stone is there in the river, or something is there, wind is there, it is making this river force, it is adding some curling force in that region. Okay, and that's how it is rotating. This proves that if I have a vector field, and this vector field, if someone tells me that this vector field has curling tendency, then in a region there is something like some other way, it has source for a vector field. This is what it is fundamental says. Means if there is a in the a certain region where I am calculating the vector field, in that inside that region, if vector field has curling tendency, and outside the vector field has no curling tendency, then inside that region there is some force that is coming, extra vector field is available, that is making the net vector field as rotating. So if vector field outside is not curling and here it is curling, it is not curling here and here it is curling, this proves that there is a vector field source somewhere inside this that is producing the curl. Okay, then only the next vector field what we are seeing in that a region is 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 has curl factor. It is similar to, I had promised that I'll bring something. So consider that I am inside a river, and river has vector field and it is not producing any curl. If I place boat here, then boat is rotating. If I place boat here, then boat is not rotating. But if I place boat here in this circular region, so here the circular region is big, then boat is moving along the river and it is rotating also. If that is the case, then there is some factor, local factor, which is generating extra vector. Like you consider this, that in this, so okay, this circular region is available. Okay, I'm just taking out, but consider there is, it is there, and then oops, I have a motor. Okay, and then you see it is rotating. Now, oops, okay, keep rotating, please. Now I have a circular region. If I have a circular region and I'm inside a river and I'm placing this motor inside it, can you see it rotating? And it is funny. Okay, so what I'm trying to say is that if I have a circular region, and outside the circular region, the vector field has no curling tendency, but inside the circular region, vector field has curling. This proves that there is something that came a rotation factor that came inside. It is emanating. It is some vector field is originating inside this circle and adding up, it is creating the curling tendency. This is what I was trying to show. It is really enjoying, right? Yeah, I believe I can sew it. Now it is better. Okay. Now this is rotating motor and I am placing inside it. Now here, okay, this is rotating motor I have placed inside it. Motor gone. Okay. And then, so there is external force, rotation force is in the local region, adding up to the new vector field that is kind of, kind of, kind of, it is generating the curl. Or take a vector field whose equation is minus yi plus xj. This example I have taken. Capital F vector field is minus yi plus xj. Then that is also a rotation vector field. Now, if you calculate the curling factor df2 by dx minus df1 by dy, then it will be 2. This proves that what is minus yi plus xj? If this is x-axis, then when y equal to 0, then it has xj. When on y-axis, when x equal to 0, then it has yi in negative direction. Net is, this is the gravity, this is the kind of vector field. If vector field is rotating, if vector field is in this direction, then it will produce curling. It will make something. If I place a boat here in this vector field, it will tend it to rotate. Like motor I showed you. So motor will generate a vector field that will be rotating one. Okay, so that is the idea. What we have learned. If I have a vector field capital F, if I have a vector field capital F, and this vector field is a gradient of any gradient vector, this capital F vector is a vector. It's a vector field. If it is a gradient of any algebraic equation, potential function, then this capital F vector is considered as path independent. Then its line integral in a closed loop will be 0. If capital F equal to grad of small f is any algebraic function. So if capital F equal to grad of small f, then capital F is considered as path independent. Line integral in a closed loop will be 0, or the curl factor will be 0. So curl of the f will be 0. df2 by dx minus df1 by dy will be 0. What is the relationship? What is the relationship between the line integral and curl factor? As per the Green's theorem, it is capital F dot dr vector in a closed loop. Integration is nothing but curl of f dA and surface integration. Stokes is saying that, okay, whatever Green is saying, it is only for 2D. Let's go for 3D and consider this force vector field is 3D. Then vector field dot dr vector, that is the line integral in a loop, in a closed loop, is equal to curl of this vector dot dot dA vector, dA vector, and integration along the surface. This is what Stokes is saying. Now, curl of f. Can I consider curl of f as g vector, another vector, where g is curl of f? If I have a vector field, if I have a vector field that is gradient of any algebraic equation, then that vector field is called grad vector and it is path independent. If I have a vector field that is curl of another vector, then it is called curl vector field. I have a vector field capital F, and capital F, the fundamental is capital F dot dr vector in a closed loop, that is line integral equal to surface integration curl of f dA, that is Green's theorem. Stokes theorem is curl of f. If it is 3D, curl of f itself is a vector, curl of f dot dA vector. Now curl of f, if I consider this as g vector, the curl of f, if I consider this as G vector, then G vector is considered as curl vector. Curl vector field means if I have any vector field G, capital G, for which there is another vector field exists and relationship is G equal to curl of F. If I have a vector field capital F and if I calculate curl means rotation tendency, if that rotation tendency, whatever it computes, that is another vector and that is equal to capital G, then capital G is called curl vector field. So capital F has two relationships now. Capital F is gradient vector of any algebraic equation and curl of capital F is G. So G is called curl vector field. Okay, if that is the case, then the line integral we are talking about capital F dot dr vector, line integral equal to surface integral, then curl of F dot dA vector, curl of F if I consider another vector G, then G vector dot dA vector surface integral. If I have a vector field G and then I make surface integration. Earlier we were making line integration. If I make surface integration, this is called flux. We will talk about flux. What is flux? Consider there is a water movement and water has a velocity. Water has a velocity. And there is a surface like this and water is passing this surface. Water is passing this surface. If water is passing the surface, in 1 second, how much water has passed this surface? That is line integral of this water, water along the surface. If water is meter per second, then multiplied by area, that is meter square, then it is meter cube per second. So if I do line integral of a velocity vector field along a surface, it gives me flux. Flux means how much mass of the vector field that cross the surface in a unit time. Makes sense, right? If I have a water as a velocity vector and if I calculate the line integral along a surface, then surface integral along a surface, then it will give net volume of the water that is crossing the surface. So capital G, that is curl of F. We started with the FDR, right? FDR line integral equal to curl of F dot dA vector, Stokes theorem, integration over a surface. If curl of F is another vector G, then G dot dA vector, if G is a kind of a vector field, then it is called surface integral and it calculates the flux. Flux is the net amount that passing through a surface, that is line integral surface. Okay, whatever it is, we will see it. Now what relationship, what we are seeing for being path independent, the line integral of vector field capital F has to be 0 in a closed loop. It is possible if capital F is gradient of small f. Okay, now this line integral is surface integral of curl of F, where curl of F, now left side is 0 because it is capital F dot dr line integral in a closed loop. If capital F is gradient vector of any algebraic equation, if I replace capital F with grad of small f, then full term is 0 because path independency, then a to a or in a closed loop line integral will be 0. If line integral is 0, then that is equal to surface integral of the curl of f dot dA vector as per the Stokes theorem. This proves that curl of f will be 0. Curl of f, where capital F is gradient of small f. This proves that the curl of gradient of small f is always 0. If I have any algebraic function small f, if I calculate gradient vector of it, and then if I calculate curl of it, df2 by dx, df1 by dy, df2 by dx, df2 by dx minus df1 by dy, where f1 and f2 constitute to capital F, and capital F, the capital F capital F is gradient of a small f, then curl of capital F it will be 0 if capital F is gradient of any gradient vector of any algebraic equation. This is what one thing we saw. Another thing what we are seeing is that the Stokes theorem is converting into flux. Gradient flux means the curl of any vector field capital F. If I consider this as a G vector, then G vector is a curl vector. Then G vector dot dA vector in a surface integral is it is called flux. It is called flux. Okay. But if I consider that I am calculating this flux in a surface that is closed, means we will discuss more about this when we talk about flux. Okay, so I'll take a closed surface. How I can take? Consider this is a closed surface. This is a closed surface. You can see this is open from this side. Now I closed it. This is a closed surface. Now, if I calculate the kind of surface integral of a vector field capital G, if capital G is a vector field for which I am calculating the surface integral along this full surface which is closed, and this vector field is a curl vector field. Now I won't reiterate what is curl vector field. If this vector field is a curl vector field, and for this curl vector field capital G, if I am calculating the surface integral capital G vector dot dA vector integration over a surface, then it will be 0. Isn't it the same what we were talking earlier about the 0 as line integral? Okay, so if it is so, what we have learned, I will see this again. If I am calculating flux, net flux, that is surface integral of any vector field. If capital G is a vector field for which I am calculating the net flux, then capital G dot dA vector surface integral. If capital G happen to be a curl vector field, then G I can replace with curl of F. Curl of F dot dA vector as per Stokes theorem in a surface integral will land up into line integral. That is F dot dr and integration in a closed loop. This proves that the surface integral of a vector field, if that vector field is a curl vector field, then it will land up in a line integral of a line curve. Where is the curve? If this is the surface, then there is only one open curve. So if I calculate line integral, means the net flux that is passing through this full surface is only dependent upon the line of this surface. This surface is a oriented surface. It has normal vector. Okay, this is little complex, but we will talk in a flux. Post this curve, we have flux. So what is Stokes is saying that if I have any vector field capital G, and capital G is if I am calculating the flux surface integral, that is flux, then if capital G is a curl vector field, capital G equal to curl of F, then Stokes theorem will be replaced as curl of surface integral will disintegrate into Stokes theorem, that is curl of F dot dA vector in a surface, that is nothing but F dot dr line integral. If that is the case, then line integral is in a circular loop. Means this surface, if I am trying to calculate the surface integration of a vector field capital G along this surface, and this G vector is a curl vector, that is curl of F, then it will be dependent only upon the whatever the curve it has, not on the surface. The surface is gone. If there is a surface and surface has a one open end and there is a curve, then this this surface integral is finally dependent upon the curl vector, that is G is curl vector of curl of f, then f's line integral along the curve. Is it not the same as if I have a vector field capital F and capital F is happen to be gradient of a algebraic equation, then it only depends upon the lower end and higher end of the line integral, not on the path. If I am calculating surface integral and of a vector field, and that vector field is happen to be the curl vector field, curl of some other vector, then the surface integral is not dependent upon the surface but line integration of any open curve. So these are the fundamental. I'm really sweating. This is that powerful. Okay. Now can we calculate that how much is the surface integral of this closed surface in a vector field capital G when capital G is a curl vector? So capital G dot dA vector in the full surface is what we are trying to calculate. Now let's draw a line here. Can we draw a line here? Okay, I'm drawing a line here. Okay, and now if I'm drawing a line here, if I'm drawing a line here, if I'm drawing a line here, then there is one half this side, one half this side. This is surface 1, this is surface 2. What is the surface integral of surface 1? Or if I talk about the Stokes theorem, if I talk about the Stokes theorem, then what is the line integral of this line, where this line belongs to this surface? Green's theorem, upward is Stokes theorem. So if I have a line and this line represents this surface and opposite line represent this surface, makes sense, right? If this line represent this surface, then opposite line represent this surface. Makes sense, right? If I have a rectangle and in this rectangle I have two loops, there is one loop, there is one loop like this, and there is another loop like this. If I take counterclockwise, then this is the direction for this loop, same as this direction for this loop. But here both are anti to each other. One side it is going like this, and other side it is coming down like this. So if I take a line, if I draw a line here and take left surface and right surface, if this line is counterclockwise, then it represents this surface. If it is clockwise, if it is counterclockwise, if it is clockwise, then it represents this surface. What is the line integral of this counterclockwise? Then line integral of this counterclockwise as per the Stokes theorem is nothing but surface integration of this curl of a vector field. If I have a vector field capital F, if I have a vector field capital F, then curl of capital F dot dA vector surface integral is nothing but F dot dr vector. So F dot dr vector for this line, okay, that gives me the kind of curl of F dot dA. Curl of F is another vector field G, line surface integral along this. If I calculate the line integral in opposite direction, then it gives me surface integral of this. Since they are same curve in opposite direction, their line integration addition will be 0. What I am trying to say, that line integral of a counterclockwise, if I do line integration in counterclockwise, it comes to some value. Same curve, if I do line integral in clockwise, then it will give negative value. If I add both, since it is same curve, it will be 0. But the line integral of a closed curve is nothing but surface integral of the curl of that vector field dot dA vector, that is the Stokes theorem. So we are calculating curl of F. Curl of F, if I consider as a G vector, that is a curl vector, then G dot dA is surface integral. So we are unknowingly we are trying to calculate surface integral of the left side, surface integral of the right side. If I add these two, that is clockwise integration of line integral in this direction, anti-clockwise line integral, this sums to 0. So the surface integral this side and this side, if I sum it, then it becomes surface integral of a closed loop. So surface integral of a vector field capital G in a closed loop is 0 if capital G happens to be a curl vector field. I mean, it looks like horrible. We will see in the flux system. Okay, so but it's a big thing. If I have a closed circular region and vector field is path independent, then in a closed region, closed curve, the net line integral will be 0. If I have a closed surface and the vector field happen to be a curl vector field, then the surface integration will be 0. Then net flux or the divergence that we will see, very powerful divergence, will be 0. Means it is, if I have a surface and there is a vector field, then it is just passing through, and whatever the surface integration is coming all along the surface, they are nullifying each other. Amazing, man. We will see it. So kind of how we will proceed from flux curve to flux. So that we will see.